Okay, welcome everyone. Thank you for coming to the last day. I already mentioned several times in this this little workshop, Raquel Perales is here to tell us about some work, and the talk is titled Semicontinuity of Capacity Under Pointed Intrinsic Flat Convergence. Please go ahead.
Thank you. Thank you for the invitation, and I apologize because I didn't have much time to prepare this talk, but luckily this is the worst talk that you will hear from me. So only good things will come in the future.
I'm sure it will be fine.
Okay, and well, my collaborator, Jeff Joreway, always gives a very nice talk that is more related to like DR. And what I'm going to present here is more like intrinsic flat part of these results. So if you wonder about these other applications for this main theorem, please look at Jeff's videos. Okay, so with that in mind, first, what is capacity? And for Rn, I'm going to write capacity in the following way. So let's consider K contained in Rn, and this is a compact set. And then we define the capacity of this set K, and let's write non-empty as the infimum of the energy of some functions. And here I'm going to write dimensional constant. So this is actually the volume of the sphere of dimension, I think it's n-1 multiplied by n-1. Anyway, this is a dimensional constant, Cn. And then we integrate the energy of these functions. So it's gradient of phi squared dx, and this function phi, well, goes from Rn to R, is going to be Lipschitz. It's going to have bounded support. And we want it to be equal to 1 around a neighborhood of K. Okay, so this is my definition of capacity. And then what we are going to do is study capacity under sequences that are converging. And there is one nice result, but this is in the very, very smooth case. Well, smooth case in comparison with intrinsic flat convergence. So imagine that I have a manifold, a fixed manifold, and then there are different Riemannian metrics defined on this manifold, such that Gi converges to G0. Here I'm also writing from 0 to infinity in C0 sense. So with these conditions, then for any K contained in our manifold M compact, non-empty, we will have that the capacity of this set K, and now we have different Riemannian metrics, so I'm going to write Gi. So this, the lim sup of these capacities is going to be less or equal than the capacity of K when I use the volume given by G0, the volume measure given by G0. Okay.
I have a question.
Mm-hmm.
Does phi also have to like go to infinity and infinity, or
This phi, what, sorry?
does phi have to reach infinity at infinity or reach some value?
No, and actually I mean, this phi, we can always, we can always truncate our phis, and our phis are always going to be between 0 and 1.
Phis are between 0 and 1. Okay, and do they reach 0 infinity?
Yeah, they have
And-
support.
Oh, bounded support. I'm sorry. I understand now. Sorry, my apologies. Okay.
Yeah, thanks. Okay, so this is
Is the M here always Rn here?
the M in this observation. No. They can be Riemannian manifolds.
Okay, all right.
Mhm. Mhm. Okay, so now what we are going to do, so goal, instead of working with MGIs, we will work with some XIs, DIs, and there will be an integral current. And as you can notice, here this space doesn't have, as in this case, the same fixed topology. So since we won't have the same fixed topology, we cannot choose a fixed K, okay? So the easiest case will be the following one. And instead of K, choose KIs, and the easiest case is going to be when we have a ball around 1 point pi and some radius r. This is going to be contained in Xi, and we will require pointed convergence and maybe I don't have enough space here, but we are fixing this and we will require pointed volume preserving intrinsic flat convergence. So this is the goal. Study a sequence that converges in this way and show this result for sets Ki, and the easiest case will be this. And so for other cases, the KIs are called defining regions. And I'm going to explain what is these defining regions. Okay. Questions?
Yeah, I have a question. Is there some obvious situation that I should have in mind where the observation that you wrote down, you have a strict inequality? There's actually a jump in the limit?
With this case, I don't know. I mean, in our case, we have examples in which if you don't require the volume preserving condition, then there will be jumps.
And when do you expect to have a jump? What happens to the set that makes you think you have it? I'm just wondering.
Yeah.
One example that can happen is you have like a cylindrical end forming in the limit. So if you actually have a cylindrical end, the capacity of every set 0 you can show.
Okay.
So if you have something kind of, the end geometry vanishes except for a cylindrical limit.
Thanks, Jeff.
Thanks.
Okay, so let me continue and let me give you one first definition. And this definition is pointed intrinsic, a sequence converging in pointed intrinsic flat sense. And this, I mean, in the paper by Wang Li and Sormani, they said that their sequence converged in pointed intrinsic flat sense, though they didn't write the definition. So here I'm just going to write the definition. And so what we're going to have is this sequence. And I didn't tell you, but these TIs are going to be integral currents. And now these are currents which are local currents. So these local currents were defined by Lang and Wenger. And so here actually I'm defining what is an integral current space in this case. And we also require, so this is definition first of integral current space in this case, or local integral current space, which is just the adaptation of Sormani-Wenger of integral current space, and set of Ti equal to Xi. Okay, so we have this sequence of local integral current spaces, and we say that Xi, Di, Ti converges in intrinsic flat sense to X dt if for any positive number, and let me call these spaces Ni, so I don't have to write much. So these are Ni's, and this is another N. If for each R greater than 0, there exists, or let's say R0, there exists an R bigger or equal than this R0, such that, and it's pointed, so let me attach the points here. Such that, okay, so when we restrict these currents that are local currents to this ball or these balls, they have to converge to N restricted to the corresponding ball. And this in intrinsic flat sense, in the sense that we know by Sormani and Wenger. Okay, and also we require, once that you put this in a bigger space where the flat convergence is realized, so that's the thing. And notice here that we are not saying that we are embedding all the Xi's in a big space set. Okay, so basically in this definition, the set in which we embed these restricted currents. So in this set, we are just embedding these restricted currents. So a priori, this set could depend on this R. And with this definition, we prove that that actually any limit is isometric and current preserving. Okay, so this is a well-defined notion of convergence. Okay, and now let me start talking about energy for integral currents. Okay, and this started with a work by Jim Porteous, where he studied semi-continuity of eigenvalues. Okay, so what one can do is define, so given an integral current space, one knows that T generates, or that one has the mass measure. Actually, we don't need this. Oh, I want to erase, and I have my eraser in. Okay. T, so let's fix a T here. Okay, then this T is a measure. And one can define, actually I needed Dn, so sorry, let me write n equal to x dt. So the energy of a Lipschitz function is going to be given by the integral over x. And here I write dx x f squared. And then here with respect to this t, okay? And now the only thing that might be strange is this. So this is called tangential differential of f. And here I'm assuming that f is Lipschitz. So if f is Lipschitz, this tangential differential exists almost everywhere. And moreover, what one knows is the following. So one knows that the norm is bounded by the Lipschitz constant of my function f. Mm-hmm. And basically in our proof, we don't need to know what is this tangential differential, but if you look at our paper, at the end of our paper, we explain what this is, and what we use is just this observation. Mm-hmm. Questions? Okay, so then with this at hand, with this energy, we can define as before, and I think I should move this way, we can define the capacity of a compact set in X. Mm-hmm. So instead of writing here the gradient of f, we just write the norm of the tangential differential, and this definition only takes into account Lipschitz functions, so that exists in a metric space, compact support and blah, blah, blah. So these conditions don't impose any trouble if we are in the metric spaces or integral current spaces. Okay, so now let me state the theorem that we want to prove.
Wait, can I ask a question?
Yes.
So am I correct in understanding that in this generality, you also have a like Hausdorff measure?
I mean, we have this T double bars measure, and what we know is the following. That T is going to be lambda multiplied. This lambda actually depends. Well, lambda is a function. And then we have the multiplicity function. And then we have the Hausdorff measure. And if this is T is of dimension M, this is of dimension M. And this is just restricted, I mean, to the set of T, which actually we are thinking is X. Mm-hmm.
Oh, okay. So you could define energy using either measure and they're basically the same. Is that correct? Or they're I mean,
I
okay,
mean, the
yeah, I'm not-
multiplicity function is
Okay.
integer, so maybe there you don't have a problem,
I
but
see.
this lambda, I don't know. I mean, this lambda could, I don't know if that would be the same. Yeah.
Oh,
I
does
mean, this-
lambda depends on the lambda changes point-wise, or?
Yeah, lambda changes point-wise. Lambda is telling you about the tangent. So if you were in a manifold, well, it's the tangent space. I'm going to write it like this, but it's the tangent space at each point. So if you have a manifold, this lambda is going to give you 1. But if you have something, I mean, these X are just rectifiable metric spaces. So then this lambda could vary according to how the tangent looks like. How the tangent space looks like.
Yeah.
And it's defined almost everywhere. Yeah, because in some points you are not going to have tangent spaces.
Dimitri, you can read more about this in Ambrosio Kirchheim's original paper.
Okay.
They show the mass measure has this format. They have a definition and then they prove this.
And I mean, this is bounded. There is a universal bound that depends on M, but besides that, and it's two sides bounds when it exists, but you don't know more about this unless you really know your space. Okay, so good. So now the theorem. And I guess this is theorem 17. So let xi, di, ti, pi converge in pointed BF sense. And then, wait, I don't want to miss any. For any k, compact. No, sorry. This is the Ball's case. And I'm going to call this Ni and this N. And let me just check if I'm not forgetting some hypothesis. Well, and we are assuming that that for this R, is compact. Okay, so then we have that. That's theorem 17, which actually is the first theorem that we have in the introduction of our paper. And then theorem 18, which is the thing that I tell you deals with these defining regions, is the following one. So under the assumptions in theorem 17, I mean only the first part. Now assume that for all r greater than 0, these currents behave in this way. So the boundaries have mass that is bounded, okay? Then for any k as before, so bounded, compact, oh sorry, compact non-empty, and contained in our limit space, one, will there exist the corresponding regions Ki containing Xi, which are going to be bounded. And the following is going to happen. And lim sub, well, actually, yeah, what we expect. Okay. This is up to a subsequence, but I'm not going to write the subsequence. Okay. And now how does one prove these two theorems? Well, these two theorems actually
Raquel, is there some sense in which the KIs converge to K?
Jeff, do they converge?
Yeah, I believe they converge to K in the intrinsic flat sense. This originated, Dan, in our paper together on the semicontinuity of mass. Yeah, and if I recall correctly, the KIs converge in intrinsic flat to K.
All right, thanks.
Okay, good. And okay, and so how does one prove these two theorems? Well, one proves these two theorems using this theorem 19. And this theorem 19 is the following. I mean, remember what is capacity? So the capacity is this infimum of the energies of Lipschitz functions that satisfy certain conditions, right? So what we're going to do is, given a function, a Lipschitz function defined here in this limit space in X that satisfies the condition so one can infimize. So we want it to be equal to 1 around a neighborhood of K and bounded support, We want to construct functions in the spaces Xi that satisfy the conditions such that we can take the infimum of that function, or that function is a candidate for the capacity, for calculating the capacity. Okay, so this is what we are going to do. Given a function, Lipschitz function here, we want to construct Lipschitz functions in this order space. And I will also have to tell you what these K's are. Okay, so let me just start with these definitions and tell me how much time I have.
You have
30
about a
minutes.
half an hour.
Okay, so then what we're going to have is the following. A function u that goes from X to R such that the Lipschitz constant of u equals 1. And K, this set K is equal to the following set, okay? And we want u to look like a distance function outside of K. So outside of K. So this type of function, we call it a defining function for K. So this is definition of defining function for my compact set. Okay. Once that I have this defining function, we are going to do the following. It's in this direction. So this is theorem 19. Okay, so actually what we're going to do is now translate our intrinsic flat result to a result in which we have a fixed space, metric space, and in this metric space we have these currents, and then these currents, instead of converging in intrinsic flat sense, we will require that they converge in weak sense, which is, yeah, in weak sense. Okay, so then theorem 19, let y equal to W star separable Banach space. And don't worry, you just have to consider, if you want, you can just take y equal to L infinity. Okay, so this is our space. Suppose that our current, we have a current here. And T, it's a current different than 0. Okay, so then we can construct our space N, which is going to be S, D. D is the distance coming from Y, so the restricted distance, and T. So this is going to be our integral current space. And here S is the set of our current. Okay. Now we have this compact set K contained in S and non-empty, compact. Okay. And we have U, and now this U from S to R, it's a defining function. And what we are going to do is going to define a function U, which is, this is just the extension of U lowercase to U, well, extend U lowercase to a Lipschitz function in the whole space Y. And this is the standard Lipschitz extension of U. Okay, and let's take the function F, which is going to be Lipschitz with bounded support, contained in, well, defined on S. And for simplicity, we can always consider is between 0 and 1, and F equals to 1 on a neighborhood of K. Okay. And now, so this is a very long theorem, but I think it's good to read it together, or to write it together. And because this is also very technical proof. So assume, well, since our function has bounded support, the support of F is going to be contained in some ball. And we will choose 0, doesn't matter. So this set 0, sorry, is just a point in Y. We don't worry about it. And we are going to choose this R0. So choose R0 such that this is 3 times the diameter of K. union Z0, in case Z0 is not, well, it's outside of S, for example, and then plus the distance between K and S minus K. Okay. Now, here we are just fixing this T, but we want a sequence of TIs converging to T. So let me write the next part of this long theorem. So suppose that TIs, well, they should be also defined in Y. Here I should have mentioned that M is greater or equal than 2. And then assume that Ti converges to T weakly. And weakly here just means, I mean, these are linear operators. So apply this to some omega, and this Ti omega should converge to T omega. These omegas are tuples of Lipschitz functions. Okay, so weakly convergence or weak convergence. And then the volume preserving condition is going to be transformed in this way. So we assume that for all R greater than 0, there exists some set B open such that it contains these poles, or this pole C0R, such that these masses of this set B converges to this mass, mass evaluated at set B. Okay, and once again we introduce the notation Ni, in which is going to be Si d Ti. This Si equals the set of Ti. And now for the defining sets, the Ki's. So take alpha I, a sequence of numbers that are going to be positive and converging to 0, and we define the Ki's in the following way. So we want them to be sets in Si, which is the set of Ti, right? So we want to take these sets here. And then what I'm going to do is intersect it with U, which is the function that is defined in Y, inverse minus infinity to alpha I. Okay, so then these are the corresponding sets. Okay, and then with these conditions,
Don't roll it up. I didn't get a picture.
sorry,
Please scroll it back down for 1 second. Thank you.
Okay. Okay, so then what happens? Number one, the Ki's by definition are contained in Si, but they are closed and bounded. Number two, remember that here I chose a function f that corresponds to this set K. I mean, we can use it for the definition of capacity, right? So then what one says here is that there exist these Fi's, which are going to be Lipschitz with bounded support defined in Si, and they are also going to satisfy that they are between 0 and 1, that they are equal to 1 on a neighborhood of Ki. And moreover, we can control the Lipschitz constants of these maps. So Lipschitz of Fi is going to be less or equal than 1 plus 3 times Lipschitz of F. And number 2b, we know where the support of Fi is going to be. So, and this is, remember that we have a point set 0, and we chose an R0 very carefully, so this can happen. So this is R0 plus 3. And then the nice thing about it is that the lim sup of the energies of the functions that we will be constructing is going to be bounded in this way. So this is capital N. Questions? So this is the theorem.
So this is the key theorem being used to prove the previous theorem.
Okay, and now let me just explain what we're going to do. We're actually, instead of proving this very nice condition, what we are going to do is choose an epsilon. And for this epsilon, so we choose an epsilon greater than 0. And for this epsilon, we construct these functions Fi that depend on this epsilon. And, oh no, this is the one that is given. Okay, and what is going to happen is that here we will get an error, and this is going to be some 4 epsilon, okay? So this is actually the proof, and then one does a diagonalization trick to get really this theorem 19. Okay, so I'm going to explain how to prove things using this or getting this error, but I'm not going to write the epsilons here because otherwise everything gets very messy.
Well, can I also ask a question about the theorem?
Yes.
So what about the distance preserving, or like, okay, what are the distance functions on the Ni? They come from Y, or they come from
Distance functions. They come from Y, yeah. Because remember, when you calculate intrinsic flat convergence, you isometrically embed. So then the distance is basically the distance in your space without isometrically embedding is going to be the same. I mean, the restriction of the distance, because it's an isometric embedding.
So if one can find isometric embeddings into this Banach space, then you can apply this theorem. Yeah, is that the idea? Okay.
Yeah. I mean, though, remember that in my definition of pointed intrinsic flat distance for locally integral current spaces, I'm not saying we have an embedding of the full space.
Sure.
So we have to work with embeddings in a big ball. We embed this big ball, and then, which you can do because K is compact. So you basically are worrying about functions that are equal to 1, yeah, in a neighborhood of K. Okay, so how does the proof goes, or idea of the proof, because this is now very technical.
Maybe it helps a little. This, in my talk, I referred to a space Z, the common space Z, And
Mhm.
Z always is actually separable, and you can use Kuratowski to put it into L infinity. So there's always this L infinity. I just never usually mention it.
Yeah. Okay, so first, what we are going to do is the following. Well, one shows using the definitions that the KIs are bounded. They are closed by definition. Just remember that I define them as this. This is closed, and I guess I'm assuming SI is closed. Well, I mean, you show first that the KIs are bounded. And then the next thing one has to do is show, or actually start, this F is just defined, remember, in S, which is the set of T. So we are going to extend this function F to a neighborhood So we extend F and we define it equal to 1 on Notice that F is defined here, so I want to define it in this piece or in the complement of S inside here. So I'm just going to write equal to 1 there. And then I say that with this definition, I mean, because I'm saying that there exists some gamma, which is small enough, then this is going to be a Lipschitz function, okay? And now what I want us to do is start looking at this paper, because our paper has the pictures, which I think are going to help with how does one define this, okay? So this is the picture. Oh, are you seeing the picture? You see the picture, right?
Yes.
Okay, so basically what I have here is, this is the set K. And then what you can see is we have this set O. So this set O is where our function F is equal to 1, okay? So we are choosing a gamma small enough. So this is such that this set, which is U inverse from minus infinity to gamma, is going to, if you intersect it with this set, you will get a piece that is still in O, okay? And now what we do is we put 1 in this set. So here the function is going to be 1. Here our function is defined and is actually 1, our Lipschitz function. And outside, well, we don't know, it's between 0 and 1. So this is what we are doing with our function. Okay, questions? Yeah, is this clear? Okay, I guess that's clear, right? I can explain again the picture if you want.
Yes, explain again the picture. Sorry.
Okay.
Yeah, in
I was
particular,
muted.
what
I was
are you
muted. I
describing?
thought, yeah.
Okay, so
Yeah.
I mean, why this this makes sense. I mean, this meaning defining f equal to 1 on this part, why it's a nice defined, a well-defined function. Okay, so then look at this. So this is S. So this is the set of our current T. And then our function f is defined in here, in this one-dimensional thing. And actually, our function f equals 1 in a neighborhood around this set, which is K. And let's think of this neighborhood as this set. So this is O. So it's actually,
that's all the way. Okay.
yeah, so our function f equals 1 on all this open set, which contains K. And then we choose a gamma small enough such that the capital U inverse of minus infinity gamma, so this set is going to actually, I mean, it's not going to be that big, right? So in this part, we define our function to be equal to 1. Okay, so actually it agrees because remember, f equals 1 here, actually f equals 1 up to here. So then writing f equal to 1 here makes sense.
And what were the properties of little u?
Of little u,
Yeah.
little u is the defining function. So it's the one that is distance to k, outside of k. So,
Okay.
and it's k equals this level z, or this region. U is Lipschitz, and the constant Lipschitz equals 1.
Wait, so just to clarify, so are you so just to understand why you just told us what you just told us, are the FIs the restriction of this extension to the sets SI or something, or?
Yeah, we are going to construct, so notice that f is just defined in this part. So what we are going to construct is an f that is going to define in a larger, I mean, it's going to be defined in some portion of y or in all y. And then the FIs that we are going to construct are going to be this new f restricted to some portion of now SI, which are the supports of the TIs.
Okay, thanks.
Yeah, so actually our KIs now look like some things that are going to be, so remember the definition of KI equals U minus 1 minus infinity alpha I intersected with SI. So these KIs are very close to this K and lie in this part. So yeah, they could look like this, right? So these are going to be my K's, I's. And actually they are going to be bigger. So I need to tell you what to do with the rest of F. I mean, I already told you what happens to F in this region. And now I need to tell you how I'm going to extend F to this part. Okay. And okay. So now let me just continue. And I'm going to show you the next picture in our paper. So I told you, I know, or we already know how to extend F in some neighborhood in this part. So now I need to know what I'm going to do with F in this extra part, okay? So now, remember that this S, here, this is S prime, but S prime is actually S intersected with a ball center at Z0 and some radius R, and this R is between R0 plus 2, R0 plus 3. Remember that I chose some R0. Okay, so I'm just looking at a smaller piece of the set of my current. And in this part, because this is the set of a current, this is countably rectifiable. So actually I have by Lipschitz charts. So what I'm going to do is cover these pieces. So these parts of S, I can take really, really tiny AIs. These are called AIs, or well, ALs, such that these ALs have nice by Lipschitz charts. And I can take, and I'm only going to take, I don't need to cover the whole thing. I'm just going to choose a finite number of them, but that have volume or mass very close to being this entire set. I mean, mass very close to S prime. Okay, I'm going to show you the formula soon. And once that I have these nice by Lipschitz charts, what we are going to do is take the tubular neighborhoods, and now these tubular neighborhoods are going to be in Y around these sets AIs. And these are what we call VLs. And then what follows in our construction is that we are going to define F. So what follows now? What F does in each AI. I'll show you the formula. And once that you have this, you will extend in the natural way of extending to these two tubular neighborhoods. And then we will construct our function F as here we have defined our F. So actually in the union of the VLs, which is going to be in this part. And with the other procedure, we know what happens here inside or in a ball around K. Okay, so this is what is going to happen. Okay, now let me show you the formulas. Or questions up to here. This is very technical, but I wanted to do it once in my life. Okay, so then, as I told you, let's look at the formulas. So we have our center set 0, and we are going to choose a ball of radius between R0 plus 2 and R0 plus 3. And this is what we are going to call W prime. And then we restrict our set to this ball intersected with S. Okay, and then let me just skip these things. But what it says is the following. We will have sets AL as I told you, that are by Lipschitz images of a compact subset of Rm by countably rectifiability of S. And then what we are going to do, what we can do is that each set AL, we can either have it in W or outside of Y minus W. And here, I'm sorry, but here we have smaller ball, and here we have a bigger ball. So actually we can separate it. Either they are in this part or they are outside this part. Okay. And now, what else do we require? The AL are pairwise disjoint. they are going to be far from this ball that we have here. So look at this, they are disjoint from this ball, which is the U inverse of minus infinity gamma. And then what I told you before is that the union of these ALs, so we are going to choose a finite number of them. And this finite number of them will almost cover this part, which is the part that is outside K delta. So this part we are almost covering with these sets AL. Okay, and then what we are requiring is that these ALs have to be really, really tiny. I mean, you chop them off in such a way that this norm of the tangential differentials, well, as I told you, these tangential differentials are bounded by the Lipschitz constant of the function. Okay, so here it is. But they are, the ALs are chopped in such a way such that this is, I mean, that basically we just have this error. Okay. So those are the properties of the ALs. And now what are the properties of the VLs? VLs, as I told you, are the tubular neighborhoods around AL. All of them are contained in this ball W prime, which we are only focusing on W prime. We don't care about what is happening outside. And it's going to be the same as the AIs. These tubular neighborhoods are either in W or in W prime. They cannot be here in the middle. And then, yeah, they are pairwise disjoint. They are also far away from this ball inside, in which I already defined our function f to be 1. And then they have this, I mean, they are very thin, right? So I'm choosing a very thin tubular neighborhood. So the mass of the union of the VLs minus the union of the ALs is very tiny. Okay, and now we do the construction that I told you. So let me just finish telling you how to construct the function quickly. So this is the lemma 2020.
I have a question. I'm sorry. You said the mass of the union, just that part.
Yes, that the VLs are very thin.
The VLs are very thin. When you say they're tubular neighborhoods, are they tubular neighborhoods sitting in the L infinity kind of space?
Yes, but remember that these tubular neighborhoods, they are going to have a tiny part here and a tiny part here.
Okay.
So I mean, the measure here is going to be 0, right? Because this is outside of S. But then they will have some measure here and some measure here.
Yes, I understand. Okay, thank you.
Okay, and now, as I told you, how do we construct these functions F? And this is lemma 2022. Okay, so this lemma 2022, it says, yes, indeed, we have a function f hat that is going to be defined in the whole space. The Lipschitz constant, as I told you in the theorem, is going to be 1 plus 3 times the Lipschitz function, the Lipschitz constant of the original Lipschitz function. F hat is between 0 and 1. And then this is the way we are going to define it. F hat agrees with F. Well, first we have to define it here. And then F hat is going to agree with F in the union of these ALs. And it's going to agree with F in this part. So, and this is basically what we did, right? In this set, it's 1. And then we know how the Lipschitz constants of the VLs of f hat restricted to BL is going to be bounded by the Lipschitz constant of f restricted to AL, and f hat is going to be 1 on a neighborhood of Ka, which is what we want, and we want also the support of this function to be contained in this pole. Okay, so now how do we choose, or how do we define f? Well, we define f in the following way. First, for AL, remember that our function f is defined here. Okay, so in a point here, I know what f is. So I'm going to define f as this way: f of a plus this thing. Oh, sorry, this is the extension to BL. And then what we have to do, since this, remember, these are disjoint, well, we can define a function in the union of all of them. And it's just going to be this function, this extension that we just constructed. And in this other part, and remember that these VLs don't touch this part, so we can define it to be 1 in this other region. And then extend this function, which is actually a Lipschitz function, extend it to the whole Y. And maybe the extension is not bounded, but you just use a cutoff argument and the resulting function is going to be bounded. And yeah, you can make it between 0 and 1, because in this part, the function is 1, and in this part, the function was between 0 and 1. Okay. And these are all the calculations. And then just one finally wants to show these energies converging, or this lower semi-continuity, this semi-continuity of the energies. And what you have to do is, we have this Fi's, which is this integral, and you just divide this integral into regions. So this region is the region in which we didn't modify our function. We actually didn't care about our function. Here actually our functions are equal to 0. So this part is going to be 0. In these VLs, remember these are the tubular neighborhoods of ALs, and these ALs come from these by Lipschitz charts. And there we have a very control. So we have actually this. We have the control of our Lipschitz constants. And then we have this other part. And this other part, I don't remember what happened to this other part. Let me just. Here we had to write some stuff. Oh yeah, this is the other part. Yeah, we had to write it in some funny way. And the parts that we get, I mean, the setting which we want to evaluate. And then, yeah, we actually arrived to this conclusion. And this has very small volume. And so putting everything together, you get that this lim sup of the energies of the Fi's is going to be bounded by the energy of F plus an error. Yeah, questions. This part was very messy, sorry. And this is a very technical proof. So thanks for being here.
Thank you so much, because I really was trying to understand this technical part myself, so I very much appreciated the details.
Thanks. You're welcome.
Other
Okay.
questions?
So yeah, let's thank Raquel. Yeah, very nice. Thanks. Yeah, we you know that it was a very nice, very clear talk on a very technical part of this paper, and you know, we did not give you very much time to prepare. So let me just make sure that's clear. Okay, good, and I'll stop the recording.